Hello everyone. This is Dr. Hussain, currently working as an associate professor in SR University. Today we will discuss about different types of power electronics devices and how power electronics devices are working for different applications for the conversion of power AC to DC, DC to AC, DC to DC, and AC to AC. Different types of power conversions we will discuss. In this lecture series, I will discuss about different types of power electronics devices and what are their major features, constraints, and what are the advantages, disadvantages, we will see. Now, first, foremost thing is power electronics. It is a present research trend because everywhere the power conversion is required. And meanwhile, first, foremost topic in this power electronics lecture series is first diode. Let us talk about the diode. What is diode? What are the things are there? Everything we will see. Now, first coming to the diode, it is a uncontrolled device and it is simply connected as a p-type material and n-type material. Both the materials, this is p-type material and this is n-type material. Both the material combined, we are forming a device that is called p-n junction diode. Here junction is formed by making the arrangements of p and n combination. We will create the junction that is called p-n junction diode, and this is the practical model of the p-n junction diode. The major theme of this p-n junction diode, it will operate in forward bias condition, and it will be in completely off state in reverse bias condition. It means it will be work as like our electrical switch. When switch is on, power will come, and other switch is off, power will off. Like that, the power semiconductor diode will work. So here, exactly, if we observe here, I am going to tell you that what is the diode and what is the operation under. Now coming to the diode, under forward bias condition, it will give nonlinear characteristics. That is the thing which I have mentioned over here. And coming to that, here diodes, there are two types, which are silicon type one diode is there, germanium type one diode is there. Silicon diode, it requires minimum voltage to switch on the device, that is called 0. Maximum it will take for the switch on condition. Maximum diode voltage it is 0.7 volts, and for germanium 0.3. So that is the basic cutting voltage of the silicon diode and germanium diode. So these are the two materials we are using for manufacturing the diodes. And coming to that, next one, uh, why we are going for BZT instead of diode? Diode is a uncontrolled device, and there we are not going to control any voltage and current. Simply it is an on-off condition. Now coming to the bipolar junction transistor. Here bi means two polarities. Bipolar, two types of polarities are there in this device. That is why we are called it as a bipolar junctions. Bipolar, two categories of polarity charges are there. That is why we call it as a bipolar. And junction, here there are two junctions are there. That is why we call it as a junction. Transistors, transformation of resistor, that is called transistor. Now coming to here, BJT, it is a current control device. And here, why we are saying BJT is a current control device, it is nothing but whatever the output current, it is with the help of the input current, emitter current, we are going to control the output current, that is collector current. That is why we call it as a BJT is a current control device. And here, if you observe the BJT, there are three terminals which are collector, base, which are collector, base, and emitter. Three terminals are there. This is one type of configuration. This is another type of configuration. In this BJT basically we will design the BJT by using two models, which are first one is PNP transistor, second one is NPN transistor. There are two types of transistors are there in this bipolar junction transistor. So there are two categories. In these two categories, the symbol representation will be different. That is we showed here. And coming to their real-time application, this is the real-time application of a bipolar junction transistor. Here, this is the emitter terminal. This is next. Next one is now coming to the next. Next one is base terminal. Next one is collector terminal. These are the three terminals for the real-time application of the transistor. So this is the basic key points which we have represented over here. And next, coming to that, uh, as I mentioned in the previous slide, that transistors are two types, that is PNP transistor and NPN transistor. Now here we can see that PNP transistor, PNP means majority carriers are holes, minority carriers are electrons. That is called PNP transistor. And here P-type material, N-type material. This is the structure of the overall structure of the PNP transistor, real-time implementation of the real-time implementation of the PNP transistor. And coming to that, this PNP transistor circuital representation is I have mentioned over here. And coming to here emitter is a heavily doped N-type material device. And coming to next, collector is a moderately doped device. And N-type it is lightly doped device. So here P place and P both are heavily, I mean, majority carrier devices, and N-type is a minority carrier, very less carrier device. And now here coming to that, if you observe that, see here always we have to observe that then even the PNP transistor and NPN transistor, it has to work in active region, then we can say that BJT is a good amplifier. Here for operating the active region operation of the transistor, we are going to make the junctions will be, first one is the input side is forward bias, output side will be reverse bias. Based on this condition only, we are going to operate the transistor in active region. In active region, the transistor will work as a amplifier. Remaining stages are there. There are two types of stages, which are saturation region and cutoff region. Those are will work as a transistor. In those condition, it will work as a switch. But in this case, it will work as an amplifier. For that amplifier reason, we are going to give the connections. That is, VEB is the forward bias, VBC is reverse bias. Now, BZT is a current control device. As I mentioned that whatever the currents are there in the output current or input current, everything will be controlled with the help of, suppose let us take it as a current controlling has been done by IE. In vice versa, suppose emitter current controlling will be done by using IC. That is, IC is equal to beta times of IB. So everything will be controlled by using currents only. That is the reason we are going to tell it as a BZT is a current control device. And here another type of model is PNP is over. Now NPN. Here NPN model, there are like similarly PNP, NPN also it is having two junctions, that is junction between collector to base, junction between collector to, I mean, base to emitter. These are the two types of junctions are available, that is we can indicate it as here JCB, and this junction will be indicated as JBE. These two junctions are available. And coming to here, majority carrier devices are electrons, because emitter, N-type emitter, it is heavily doped. N-type emitter, N-type collector is heavily doped. N-type emitter is moderately doped. Base is lightly doped device. That is the reason we call it as a majority carrier devices are electrons, minority carriers devices are holes. That is why we mentioned that this is the electron majority carrier bipolar junction transistor. And coming to this structure of the PN, like similar to PNP, NPN structure is also like this. So these are the structural diagram, and this is the operational diagram of the bipolar junction transistor. Now the condition is, in the transistor, there are two types of transistors are there. Which one is referable, which one we have to use for priority based applications, those things we can see. See in this there are two types of transistors, PNP and NPN. Which one is the best one and why it is best one, we will see. PNP and NPN. Here, from the given features, NPN is the best transistor because of the reason it will give better performance, and it provides efficiency also very high when compared to the PNP transistors. And meanwhile, most of the electrons, majority carriers are electrons, and it will be used for many electronic circuit designing and amplifier applications. Most of the times we are using NPN transistor instead of PNP. That is why PNP and NPN comparison is the very important concern over here. And here in down, I clearly mentioned that bipolar junction transistor is a current control device. One of the gate examination, they have asked this BJT is a current control device. In that one, NPN is the most preferable one because it will provide good amplification factor and um, operational efficiency for the NPN transistor is very high. That is why we have mentioned over here. Now coming to the first foremost thing is in the power electronics, the major device is silicon controlled rectifier. What is silicon controlled rectifier and what is the structure? And along with that, how practically we are going to utilize and what are the ICs are available in the present market. And so coming to that, for suppose silicon control rectifier will be operated with one source, what will happen in the device? Similarly, suppose the device it will be connected in different modes of operation, what will happen and why, how we have to operate the silicon control rectifier, what is latching current, what is holding current, everything we will discuss. These PPT, it will clearly give the overall view of the silicon control rectifier. This is the structural representation. And coming to that, this is the characteristics. And this is the real-time silicon control rectifier model, industry model. And this is the overall operation of the silicon control rectifier. And these diagram will give the when silicon control rectifier will be operated in forward bias condition with one source. And coming to this diagram will give the silicon control rectifier operated in reverse bias condition when it is in gate signal will be offset off condition. So these are the overall view of the silicon control rectifier. Now come first and foremost thing is structure. If you observe the structure of the silicon control rectifier, it is having four layers: p-type layer, n-type layer, p-type layer, and n-type layer. So it is nothing but four layers are there. With these four layers, the silicon control rectifier is having three junctions, which are Pn, that is called one junction, J1, Np, that is called J2, that is one more junction, that is Pn, it is called one more junction, that is J3. So here overall how many junctions are there? Three junctions are there. These are the three junctions, J1, J2, J3. And coming to the name indicated that the terminal name is anode, gate, and cathode terminal. These are the terminals it is indicated for the silicon control rectifier. Now, in our laboratory, if you clearly observe that this is the normal testing structure of the silicon control rectifier. And here terminals are completely different when compared to this one. First, it will come here gate signal, after that anode signal, after that cathode signal. So these are the structural laboratory structure of the silicon control rectifier. And these are the terminals and this is the material of the silicon control rectifier. And this is the heat sink. With the help of these heat sinks, we are going to dissipate the heat of the silicon control rectifier for operating higher temperature applications. Now coming to that second task is how silicon control rectifier will operate when we are giving the forward voltage to the silicon control structure. First foremost thing is positive is connected to anode and negative is connected to cathode. That is here why this structure we are call it as a forward. It is nothing but plus is connected to p type, minus is connected to n type. That is why this is forward source forward condition state. Now we will check which junction is forward bias, which junction is reverse bias. Now from this plus is connected to p type. Here from this minus is connected to n type. Then junction J1 will be forward bias. Now coming to here, second junction, plus is connected here and minus is connected here. Then junction J2 will be reverse bias. Now third one, plus comes to here, minus comes to here. Then this will be connected as a forward bias. It means J1 forward bias operation, J2 reverse bias operation, J3 forward bias operation. Now our silicon control rectifier condition is the junctions J1, J2, J3 all are must and should be forward bias. Then only the silicon control rectifier comes into the conduction state. Otherwise it may not come to the conduction state. Now coming to the second one. Suppose here forward bias voltage we have considered that positive voltage. Now suppose we will take it as a here negative voltage. Here negative voltage will come. What will be the condition of the silicon control rectifier? We'll see. First, let us take it as a J1 junction, J2 junction, J3 junction. Now, first J1 junction minus it will come to here, plus will comes to here. Then J1 will be reverse bias. Now, second junction minus will comes to here, plus will comes to here. This will be forward bias. So, junction J2 will be forward bias. Now, third one minus will come here, plus will come here, then this one will be reverse bias. It means in this condition J1 reverse bias, J2 forward bias, and J3 will be reverse bias. So in this condition the SCR won't come for the conduction state. In this state it will come, but it will take huge amount of voltages. But coming to here, we are going to make a separate connection, that is gate connection. Here we are going to apply, and we are going to check how the silicon control rectifier will work along with junction J1, J2, J3, and after that we'll go for the explanation of the characteristics. Now we'll see in the next slide. Coming to that, why silicon control rectifier is preferred, and most of the gate competitive examination, the people they may ask that BJT is a current control or voltage control. BJT is a current control device. Similarly, SCR is also a current control device, because whatever the current control it is there, current controlling we are saying in this silicon control rectifier, it is gate signal. When gate current, little bit gate current will change, automatically the total current flow of the silicon control rectifier will be changes. So that is the major concern here. That is why we call it as a silicon control rectifier is a current controlling device. And it is having, as I mentioned, that it is having four layers, and four layers that act as a latching switch, and required positive small gate voltage. It is more than enough for changing the operation of the silicon control rectifier. Once the conducting, so holding current will come, then that time we no need of giving the anode, I mean gate current. Directly silicon control rectifier starts working in active region operation. Now next slide, we'll see next one. So as I mentioned previously, the silicon control rectifier is having four layers, that is called first one, second one, third one, and fourth one. How many junctions are there? Three junctions are there. Those are J1, J2, J3. Now similarly here we have to observe which device, I mean which layer is having huge amount of electrons, which is not having huge number of holes. We will see step by step. Now P plus, it is a heavily doped device, and N minus, it is a very lightly doped device, and this one is a lightly doped device, and this one is a heavily doped device. This is heavily doped device, and this is lightly doped device, and this is moderately doped device, and this is highly doped device. So in this one, as I mentioned that the silicon control rectifier having anode side as well as cathode sides are having highly doped layers are there, and in middle we are having lightly doped and moderately doped terminals are there. And meanwhile here I have indicated the structural, I mean tabular form of the silicon control rectifier, and what are the material doping levels are there, everything I have mentioned over here. And see, if you observe that silicon control rectifier, it will act as a back-to-back connection of two transistors, which are Q1 and Q2. Here Q1, Q2, for our simplicity, we have mentioned Q1, Q2. You people can mention which one is required Q1 or which one is required Q2. You can take the decision in your own way. And coming to the structural model, if you observe that first starting time p-type material, n-type material, p-type, n-type, it is there. Now here we are going to cut the pieces entire SCR will be we are going to convert it into two pieces, which are PNP piece and NPN. Two pieces are there. This will be take it as a Q1. This will be take it as a Q2. And here, this is the anode terminal and same. Just I'll show you one by one how we are going to make it as a back-to-back transistor. PNP, take it as a PNP. And here anode, we are not going to disturb anode. No, whatever the gate terminals are there directly, uh, mm, terminal, this terminal directly we will give it to the next to transistor n type configuration. And after that, what we are going to do here, whatever the gate terminal it is there, as it is you mentioned here, but p type it is connected to gate layer. Then that is the reason we have mentioned over here gate terminal. Now finally cathode terminal as it is which I have mentioned over here. This is the cathode terminal. So this is the way we can say that silicon controlled rectifier will be operated in true transistor model, that is called Q1 Q2 transistors model. So in this way, the silicon control rectifier will work as a true transistors. And coming to that, first we will see, as I discussed previously, overall layout. Now in depth manner we will discuss here. First foremost thing is reverse blocking mode of the silicon control rectifier. So reverse blocking mode of the silicon control rectifier, if you observe this, here supply voltage is reverse. It means minus layers are there. Whatever the minus terminal it is there, it will goes here, and plus terminal it is there, it will goes to here. It means minus we have to connect it to uh, plus holes material, that is called, this entire holes will come out and it will be neutralized with the electrons. Similarly here, this entire electrons will come out and it will be neutralized with the positive terminal of the battery. Then this, after certain time duration, this layer and this layer will get empty. Then after that, finally neutralization completion is over. These electrons goes to here and plus electrons goes to here. After certain time duration, these J3 and J1 junction will get breakdown. The overall device will get breakdown, that is called reverse breakdown voltage. And coming to, if you observe here, this J1 is reverse bias, J3 is reverse bias, and the only one is J2 is only forward bias. So this is the supply voltage. When the supply voltage is reverse bias condition, how silicon control rectifier will work. Now coming to the next stage, if you observe, suppose the source voltage, battery voltage is forward voltage. Forward voltage, it is nothing but plus terminal, it is connected to P type, minus terminal, it is connected to N type. It means here same polarity means this is P type means holes, N type means electrons. These P type holes directly ripples. Plus plus means a ripple will come, and minus minus mean ripples will come. This plus terminal holes, it will get ripple, and minus it will get ripple over here. Then junction J1 will be the forward bias, then junction J3 will be the forward bias, and this plus will comes to here, minus will comes to here. This junction will form it as a reverse bias. And this is the condition for, suppose we are applying forward voltage, it will take higher amount of voltages for transferring the charges from anode side to cathode side. That is why we are going to consider a gate signal voltage, that is here. Here we are going to consider a gate signal voltage. Let us talk about the overall structure and its characteristics. First, think that this gate signal is not there. Then, as we know that positive is applied to P terminal, negative is applied to N terminal. Then these holes are there, these electrons are there, it will get collide with these two, and the charges moves from this level to this level and this place to this place. So J1, J3 will be forward bias and this one will be reverse bias. I'll indicate here forward bias, and this one also forward bias, and this one is reverse bias. After certain time duration, entire holes will move towards to this, entire electrons will move towards to this. Then up to certain time duration, this entire current will move from anode to cathode. Then the current direction will be like this. So it will take too much voltage when compared to the previous thing. I mean, previous means when we won't apply the gate signal voltage. That is the reason here I clearly indicated that when the gate signal is not there, it will take too much voltage to break down the J2 junction, and after that only it will go to the current like this. This is the condition. If you people observe that, it will take too much time. Forward breakdown voltage will be very high. And here Ig is clearly indicated that Ig current is 0. It means that there is no gate supply we are applying. Now coming to that, after the condition, when we are applying gate signal, we no need to apply here much amount of voltages. That is the thing we are going to show it here. Now suppose first we will apply 10 volts here, and here we will apply 2 to 3 volts or 5 volts. Then automatically J1 forward bias, J3 forward bias. By applying this one, J2 is also forward bias. Then immediately the current flows from anode to cathode. So by applying small gate current, we can control the overall anode to cathode voltage at a different level. It means Ig is increasing. For suppose first time Ig1 is very less when compared to second stage, that is Ig1 is less than to Ig2, second time, third time Ig2 is less than Ig3. After applying different Ig currents, the breakdown voltage will come as soon as possible. And here there are two types of currents, three types of currents which we can observe. Forward breakdown voltage, that time there is a small leakage current will come, that is called forward leakage current, IB naught. And along with that, there is a two definitions will come here. What is holding current? What is latching current? Holding current, it is nothing but once the gate signal is applied, we are going to make it a small current. That definitions also I have indicated over here. You can observe that previous slide. So junction holding current, latching current are here. Holding current is nothing but gate current will be there. Along with that, we are going to apply anode to cathode voltage. Then all the junction will be latched and it will start working. Once latching is over, the silicon control rectifier continuously works up to the active region conditions. Now coming to the reverse condition, if you people observe that there is no gate signal over here, this will be removed. The gate signal will be removed, and only the signal will be that forward voltage, reverse forward source voltage side will be there, and this voltage will be reverse bias condition. When we apply reverse bias condition, J1, J3 will be reverse bias, only J2 will be forward bias. J2 will be forward bias. Here, in this condition, after certain time duration, the second junction J2 is also comes to the conduction state, then overall device will be breakdown. That is called breakdown condition, reverse breakdown condition of the silicon controlled rectifier. And these Ig1, Ig2s will increase, keep on to overcome the silicon controlled rectifier switch on time interval. So this is the overall view. We can represent it over here. With the help of these two sources only, we can draw these characteristics. And in this region, the silicon control rectifier will behave as a like a conversion device, like AC to DC, DC to AC conversion. It will be possible. And this stage, it will be leakage current will flow. Then there is a small leakage current flowing. But however, we won't operate the silicon control rectifier in this stage. Now, if you observe that there are few more devices are there in the power electronics lecture series, which are now, as of now, we discuss the fundamentals of diodes. It is an control device. BJT, it is a current control device. Silicon control rectifier is a current control device. MOSFET, coming to all, just now we discussed three devices. All most of the devices are current control device. Now coming to the MOSFET. MOSFET, it is a voltage control device. We have to remember that word because gate to source voltage which is there, whatever the voltage will be there, we are going to control with the help of gate voltage. That is called MOSFET is a voltage control device. And another name of the MOSFET, we have to remember that insulated gate field effect transistor. It is clearly indicated here. Please observe all of you. This is insulated gate field effect transistor. This is the another name of the MOSFET, that is called metal oxide semiconductor field effect transistor. Here, MOSFETs are also classified into two types, which are enhancement type MOSFET, depletion type MOSFET. In enhancement type MOSFET, there are two types are there: enhancement mode N channel type MOSFET, enhancement mode P channel type MOSFET. Channel means we have to create, the electron flow direction from source to drain. There is a channel formation will be there. That is a channel indication. N channel indication, P channel indication. Now coming to depletion type MOSFET, these depletion type MOSFETs are N channel depletion type MOSFET and P channel depletion type MOSFET. Now, if we observe that these construction of the MOSFET and MOSFET structures and how MOSFETs will work along with that different types of configuration of circuits. These are all the things we will see in the next lecture. Thank you.